I will talk about future works. We plan to work in microgrids and power harvesting loops in the future. So about us, we work in the National Electricity Operator of Ecuador, called SENACE. Our purpose is a strategic entity of the Ecuadorian electricity sector. We operates and manage the technical and commercial operation of the national interconnected system and international interconnection. We have international interconnection with Colombia Power System and Peru Power Systems. What is our strategy? We're making high-level technical and strategic decisions where to produce the energy, how to transport it, and how to deliver it at the moment it is required by the users. So summarize the Ecuador power system. We have an energy production. So we have renewables power plants about 86%. The thermal power plants is about 12%. And in the interconnection, we have 2% of the energy production. We have an installed capacity of 7,160 megawatts, and our power consumption is 4,500 megawatts. So I will talk about a little bit about the international interconnection. So since 2003, Ecuador and Colombia have been interconnected through 4 transmission circuits between the Jamondino substations and Pimampiro substation. The transfer capacity between both countries is 500 megawatts at 230 kilowatts. The power exchange between the 2 countries is limited due to different electrical constraints. So in this work, we will see the constraints and how we do control and protection schemes to separate the areas. Today, an area separation scheme is in operation, which allows detecting high risk situations. But before we implemented this scheme, we worked in digital.
I think we lost David, is that right?
I think so, yeah.
Yes.
Okay. Other colleagues, are you on the line? Harun and Diego? Okay.
Good morning to everybody. I'm Aaron de la Torre. I call David because he's connected in the other side, no with me.
Okay, no problem. We can wait. We can wait a few more minutes.
Okay, thank you.
Okay, so meanwhile, since we're waiting for David, for those of you who joined late, I shared a link, which I'm resharing again. It's a white paper on digital twins of equipment, power equipment, that was issued recently by another working group under Transmission Distribution Committee. And their focus is on digital twins of power equipment, not the grid level digital twin. But I think still there are a lot of good material to read from this white paper. So I recommend you guys have a look at that. And the other announcement that they made in the beginning was the additional call that we're going to have in April. I sent out a separate link for that. If you have not received it, just let me know. but you should have it on your calendar. I think it will be a very interesting one. It will be a presentation from Europe on their recent effort in creating a digital twin of the continental electric power grid. Okay, I think David is back.
Yes, sorry.
Oh, no worries.
The connection.
Glad to
Sorry.
have you back. No worries. Go ahead, please.
Okay, thank you. I will share my screen again.
Yeah, of course.
Okay, can you see the presentation?
Yes, yes, I see the operating rack.
The final slide is this, or I don't know.
Yeah, you were in
I
the middle of this
connection.
slide.
Okay,
You were in the middle of
so
this
this
slide,
one.
yeah.
Okay, no problem. So about the international interconnections, as I said, we have an interconnection with Colombia Power System through 4 transmission circuits between 2 substations, Samandina and Pimampiro. The maximum transfer capacity is 500 megawatts. Today we have an area separation scheme in operation, but before that, we test in the digital twin. We test the operation, the good operation of this scheme in the digital twin. It now is implemented in the real system. So within the infrastructure that SENACE has, we have the digital simulator of the Opal RT brand, which has the following characteristics. Using a Linux platform, we have 32 cores, Intel Xeon, and 61 gigabytes of RAM. Here in the Opal RT digital simulator, we have the software HyperSync. The main purpose of the Opal RT real-time digital simulator currently installed at SENACE is to perform studies and integration tests of power generation, transmission, and distribution by exploiting the software in the loop and the hardware in the loop type of simulation options. In this sense, the simulator is used by students, operators, research, and professors from SENACE or other Ecuadorian institutions to perform general studies of power system, simulate the integration and interaction of renewable energy sources, distributed energy storage system, fast SCADA, MS, and other systems. Here we see how we develop all the Ecuadorian system, but in a reduced form. So we have all Ecuadorian system model in HyperSync. We have the control systems and the logic, and we implemented logical and physical inputs and outputs here in the real-time simulator in the software HyperSync. So the next topics, WAMS-based special protection scheme. WAP protector developed by a Slovenian company Elpros is a sophisticated operational system of wide area monitoring with control and protection functions dedicated to power system with focus on the operation of the Ecuadorian power system, which has been implemented in SENACE since 2013. SENACE One Systems is currently integrated by 60 PMUs distributed all around Ecuador, which are integrated through a fiber optic network to a central PDC. And with that, we recollect all the phasor measurements. And in the system, in the WAP protector, we can do monitoring and control of the system. So now the architecture of the WAMS system. We have 60 PMUs around Ecuador. So they are connected in the fiber optical network. And additional, in the same net, we have artifacts or automatic controllers. These automatic controllers we use for model validation. We will talk about this later. And the important thing is in the same network of WAMS, we have the real-time digital simulator. So with this, we can send the phasor data in the same net, and we use the same system that are connected in SENACE. So we combine all these PMUs around Ecuador and the simulation with the real-time digital simulator. So how we do the integration of digital twins and WAMS or one system? So the system architecture, the integration of the real-time digital simulator and SENACE one system is done through two ways. One way we do with virtual PMUs that we can see here. We modeled the virtual PMUs in Hypersync, and we send via protocol. And the other way is to send with low-level signals. So we connect real equipment, PMUs, relays, or other equipments that through this equipment we can send the phasor data to one system. In the future we will integrate the power amplifier. In this power amplifier, we will connect real loads or source and perform a dynamic analysis in the one system. But this is our future work. Application of digital twin technology. So the methodology developed must have a validate model that will allow to obtain a response similar to that of the real system, for which SENACE perform field tests that, together with the optimization algorithms that we have in the Hypersync software, allow to obtain the real model of the generator system with our modeler in the simulator. So we do field tests with artifacts or automatic controllers. We register the test in the real plant, and with these test results, we model the model. We optimize the parameters, and we have the same response in the simulation and in the real plant. So we validate the model, and this model is in the Hypersync software. So how we do the hardware and software in the loop architecture. So once we have this model of all the power system with the validate models of all power plants in Ecuador, we have a validate model here that the response is similar to the real response in the power system of Ecuador. So with this model, we simulate in real time. We transfer the data, the logical data or the analog data to the PMUs by low-level signals or the virtual PMUs. And these signals are transferred to the PMU relays, and the PMU relays transfer the phasor measurements to the WAMS system. The WAMS systems process the data and do some logics of protection or control. If a condition satisfies the trip, we send the trip to the simulation by a GUS message. So with this architecture, we can test control and protection schemes that we will implement in the real power system. So in the next slide, I will show you the implementation of the area separation scheme based on WAMS. So the first step we do is define the logics. So we define three logics for the separation. The logic one is based on angular difference. As you know, we can have the angular data only via phasor measurements. So this difference angular is to determine the power transfer limits in the interconnection lines. The other logic is based on voltage derivatives. Actually, in case of critical voltage variations in the interconnection busbar. And the last logic is based on modal analysis. With the phasor data, we do the modal analysis in the HyperSync software. So we detect the inter-area power oscillation with low damping and send the trip to ensure of the electrical system of Ecuador and Colombia operates well. So here we can see that if a logic send a trip to the relay send the good trip to the HyperSync, but the logics are implemented in the WAMS system. So the WAMS system control the relay tripping, and this relay send the trip to the simulator again. So it's a software in the loop architecture, and we have hardware too. So the case of a study of the implementation. So the proposed case of study is described below. The initial condition is with 4 lines in service. The test consists of an event that causes an external zone operation and not an internal zone operation. A load increase from 245 megawatts to 450 megawatts in Pomaski substation. So with this event, we will see the oscillation of the impedance. So the impedance moves to an external zone here in the HyperSync software. In the real-time simulation, we can see that the impedance moves to an external zone. So if the impedance stays 100 milliseconds in the external zones, logic 1 operates. So the WAMS system send the trip to the relay, and the relay send the trip to the real-time digital simulator. So here we can see the response in HyperSync in the real-time digital simulator. So here the trip is sent. So we read a control file with this signals. So here we can see the trip and the moves of the impedance here in the HyperSync software. But all the control is done by the WAMS system. So the last step of this project is the implementation in the real system. Once we have tested in the digital twin system and the results were good, we proceed to implement this scheme in the real system. So how we do that? In order to provide the ability to observe what is happening in the interconnection at any time and monitor the actual behavior of the system, was implemented in the substation in Ecuador an automation equipment that allows to detect each program logic here. So the WAMS system, the application, the logic, the trips, all these logic algorithms are programmed in the controller, in a cell equipment. That is a controller, is a AirTag equipment. So this equipment do the same thing that we do with one system. So the controller send the trip to the relay, and the relay send the trip to the breakers, all the 4 circuits when logic is triggered. So here we can see the implementation in the real system with 4 relays that have the PMUs functionality too, and a central controller that send the trips, and here is the logical application running. So if detected trigger, the trigger is sent to the relays, and the relay sends a good message to the breakers here in the PMU substation, and open the interconnections and separate the systems. So this is what we did here in Ecuador with digital twins. In the future work, we will work on a power hardware in the loop in a microgrid. We will be modeled in the real-time simulation software HyperSync. So we pretend to connect in the power amplifier AMETEC, the AMETEC, we will connect an inverter of 15 kilowatt photovoltaic panel, and using a PMU, different status and variables will be recorded and monitored through a communication protocol. And this communication recording and monitoring will allow managing an optimal control of the power or the virtual power plant within a field platform. So we are working in this project. And another interesting project that we will work is in Galapagos microgrid. Here in Ecuador, we have Galapagos Islands. Galapagos Islands is a separate power system. They have a microgrid implemented. So we pretend with real-time simulations of the control system operation of the storage systems, photovoltaic systems, and conventional power plants that confront the microgrid of the Galapagos Islands in Ecuador. So we will do studies that will provide a real analysis of the behavior of the control system of all these renewable energies in order to ensure the stable and reliable operation of the microgrid. So this is all the presentation. I hope you understand all the presentation. Sorry for my English. I didn't practice my English for 2 years, so I do the best possible. Sorry.
Oh, you did a great job.
Thank you.
You're doing an
much.
excellent job. You're much better than my Spanish.
Thank you. Yes.
Perfect.
So thank
All
you.
right.
Thank you very much for your attention.
Of course, David. Thank you very much for the nice presentation. So here I would like to open the floor to questions. Anyone from the audience? You're welcome to unmute yourself, ask your question, or if you feel more comfortable, put it in the chat. I'll read it for you. I can start with a question while folks are thinking about their questions. My first question is not relevant to digital twin, but David, you showed when you introduced the grid in the Ecuador, you showed that 85% is renewable energy resources. The generation is renewable energy resources, 85%. Is that right?
Yes, that's right, because we have hydroelectric power plants. All the energy production is in hydroelectric power plant. This is because when we don't have water, we don't have production to the capability to produce energy to cover the demand. So
okay, so most part of that, yeah, so most part of that renewable is hydro. Is that right?
Yes, this is
Okay.
right. Yes, is there.
I get it.
1% is eolic, though.
Okay, get it. All right. So before asking my next question, I'll go to Reza. I see your hands up.
This is Reza Ramzan with Agile. David, thank you so much for the very interesting presentation. I have a question regarding the model validation part of the WAMS that you presented. If you can please share the screen again. I wanted to ask some questions about the parameters that are being validated in those models. My understanding was that you look at an asset, let's say a generator unit, and then using both simulation and field data, you try to validate your HyperSim models. I want to know which parts of the system, which assets you're focusing on, and what parameters are being validated against real data. Are you muted?
So here in the presentation, so in our methodology, we have we went to the field, to the power plant. We test in the governor control, in the AVR and PCS. We do several tests, like we inject with the Omicron. We inject a reference signal to IVR. The same for the governor control. We send a reference and step in the reference. So with this step, we monitor the response of the governor and the AVR and the PCs in the WAMS system. We monitor and register all the data. With all the data, we have a optimization algorithm that in Power Factory we validate the parameters. All the parameters in the AVR are the lead lag blocks and the time constant. In the governor are the gains and the PID content. We identify these parameters and try to match the field response with the simulation response. And the optimization algorithm do several iterations to match these two signals, the simulation signals and the field signals, and move these parameters, the time constant and PID constant. So,
okay, so
I hope I answered your question.
Thank you. When you're doing the Omicron test, the step tests, is the unit being taken off operation or is it online?
It's online. It's online. It's a critical test, but it's online because we always do the reference by the Omicron. Never.
So what are the levels of those step references not to perturb or impact the system?
Usually is 110 volts because it's a control signal. So we send 110 volts with a variable frequency for the governor. So we do the frequency step in the simulation, but the voltage is constant. So we do 60 hertz here in Ecuador, and we do a step about 1%, 2.5% to the governor. And the AVR is the same, but we move the voltage. The voltage is, we do a step in the voltage is the same as 110 volts here, but is with the power plant in line with load.
Very interesting. I just have one more follow-up question, and that is,
Okay.
I understand that you use the Omicron and step changes and frequency variation changes to kind of induce dynamics in the system, so your
Exactly.
algorithm can pick up the behavior of the control systems. Have you also thought about using natural, system dynamics when an event happens, or when a fault happens, when a set point change happens naturally within the network, capture those live data and use them for model validation? Is there any merit to that?
Sorry, can you repeat the question? I lose the connection.
So I understand that you have the controlled environment where you want to do some step change tests using the Omicron. But those things, creating the dynamics, can naturally happen in the system when faults happen, when load switches, happen, when there is a set point change and things like that. Is there any merit to use those type of data instead of perturbing using Omicron?
Yes, it's because with an event data, we have all the system, all these. Let me show you all these system, but with
Did we lost David?
so.
Apparently.
Sorry, can you hear me?
Yes, now we
Yes,
hear
yes.
you. Go ahead.
Yes, so.
All right, thank you so much. Very interesting. I appreciate you.
All right, thank you. Professor Polinsky, go ahead, please.
All right, can you hear me?
Yes, we hear you.
Okay. Yeah, thanks, David, for the presentation. Very nice. I'm deeply impressed that you are allowed to make experiments with with the live assets and power stations. And I'm also impressed that you can validate things, because I think it's very complex, especially when you have digital controllers and they're usually black box and nobody knows what they do. And even normal controllers have lots of parameters, so impressed. My question is about the model that we see right now. You really have the entire Ecuadorian power system in a hypersim model with all the generation units and all the controls.
We have almost all the system, but we reduce some radial connection. We maintain the principal power plants, and we have the good response in the system. It's a reduced system, but we had a very good response. But here we have a problem with the process in hypersync. So we have to decouple the system in I think 12 cores to the simulation. So a library to the so decouple the processing. So I don't know. We
have troubles hearing you, David.
Yeah, David, is there any way that you can call in? Maybe the internet is not good enough.
Sorry, the internet is not good.
But now we hear you. Go ahead, please.
Okay. So as I said, this is a reduced system. All the radial circuits are an equivalent circuit, but with this system, we have a good response that we have with the
Yeah, unfortunately.
All right. Thanks, David.
Yeah, maybe Harun, if you can ask David to call in, that would be great. I also had a question, but and again, I don't know if Harun, you can comment on this, or it should be David. I understand that the measurements are used to validate the models in the HyperSim model, but since we're talking about digital twin, and although there's no standard in definition, but the common understanding is that a digital twin is a combination of models and data somehow getting merged into each other. Do you know that if any of the simulation happening when the PMU is connected and it's actually feeding the HyperSim model? Because if that's not the case, I assume that the HyperSim model is a snapshot in the sense that the load levels or dispatch levels doesn't change. But if you have somehow model, PMU data or any other kind of data feeding the model, then it becomes live in quote unquote. Do you have any insight into that? I'm afraid that we've lost Harun as well. All right. Yeah, unfortunately, these kind of things happens. It actually happened to me when we started the call. I lost my internet connection. Okay. All right. So I don't know is there any other comment or question? We don't have the presenter, unfortunately, on the call, but any comment that anybody would like to make before we close the session? Okay, if not, we can close this session. Just a reminder that we have another additional call in April. I sent out the link, and I think it will be a very interesting presentation. So I would like to thank again our colleagues from Ecuador, David, Harun, and Diego. And yes, so I will see you next time. Thank you, everyone.
Thank you. Have a good day.
Thank you. Have a great day.
Take care.
Bye-bye.
Thank you very much.
Thank you.
Thank you.